So where we ended up in the second hour last week, we were talking about measures of center and spread. And what we're talking about is probability distributions, or just data distributions themselves. And what those are is just that curve that shows how much of each value there is. We have a number line down here showing all the possible values from the smallest up to the largest value. And the height of that curve tells you how many items take on that particular value. Now, this is just kind of a sloppy curve. Most of our curves took on what we call the normal curve, or sometimes called the bell curve, where the measures of center we talked about, the mean, median, and mode, describe the center of that bell. In a perfect distribution, the mean, median, and mode would be the same number. The other thing we needed to describe was how wide that curve was. And what we used to describe that, we used the range, which wasn't very accurate. The better description that we found was the standard deviation. And we're going to review just how that describes the width of this curve a little bit more to start off tonight. So if we have a small set of numbers, and I want to find center and spread. So I'm going to find three things here, actually. The ones that I think are the most important. I want to find the mean, the median, and the standard deviation. How do we find the mean? Okay, we add them all up. So we're going to divide by 5. Okay. This will give us, what, 15.2, I believe. Somebody double check. That's right. Cool. How do we find the mean? Or the median, sorry. Yeah, that was the mean. I'm sorry. How do we find the median? The first thing we have to make sure we have is have them in order. Smallest to largest. And in this case we do. We have them smallest to largest. What's the second thing we need to do? The location. And how do we find the location? Well, we can cross them out from smallest to largest and I'll work our way in. In a larger data set, that doesn't work as well. It's 0.5 times n. And in this case, n is what? 5. There's 5 items in the set. N is the number of items in the data set. So 0.5 times n will be 0.5 times 5, or 2.5. What do we do if that comes out to be a decimal number? We round up to the next spot. So it's going to be the number in the third spot will be our mean. That would be the 16. Or median, I should say. I'm screwing up my vocabulary. If this had come out to be a whole number, what would we have done? It would have been between that spot and the next spot. So if that would have come out to be a 3, then it would have been between the third and the fourth. But since it was a 2.5, we rounded it up to a 3. Standard deviation. What is our first step in finding the standard deviation? I'll give you a hint. We've already done it. Find the mean. Very good. The second step. We subtract the mean from each number. Very good. Now I purposely gave us an ugly mean on this one so that this step wouldn't be quite as neat as what we've had before. So we've got to subtract 15.2 from each of these numbers. Seven minus 15.2 is a negative 8.2. 13 minus 15.2, negative 2.2. 16 minus 15.2, 0.8. 18 minus 15.2, 2.8. And 22 minus 15.2, 6.8. Now what? We square it. Number squaring is times itself. So a negative 8.2 squared is 67.24. 2.2 or negative 2.2 squared is 4.84. Now you notice I'm punching these in, I'm not putting in the negative. Why don't I have to put in the negative? Exactly. When we square anything, it's going to be a positive answer. So the negative isn't going to change our result there. 0.8 squared will be 0.64. 2.8 squared. 7 point what? 0.84. And 6.8 squared? 46.24. What is step 4? We find the total. We sum those up. That's going to be 126.80. Looks to be. How about step 5? Divide by n minus 1. N in this case is 5, so we're going to divide by 4. So that's going to give us 31.7. Now what? Step 6. Square root of 31.7 is 5.6. 5.63, very good. That would be the variance. If we were asked for the variance, we would stop there. Yes. So that's our mean and standard deviation calculations from last week. So now the question is, what do they mean? What are they good for? How do they tell us anything about that curve? Well, if we look at that curve, see if I can draw a decent one. Yeah, good enough. The center, as we said, this is the center of the curve, the midpoint of the curve. The curve should be symmetrical around that center if it is a perfect or a really good normally distributed set of data. That should be the mean and the median, or the mode. They should all be in the same spot. We tend to use the mean for the center. Like I said, a good set of data, the mean and the median should be the same. And then we can go out from that mean in steps of 1 standard deviation. If we go 1 standard deviation above the mean, we expect 34% of the data to be in there. In fact, your book uses a bit more exact. It's about 34.13% of the data that we expect to be in that range. If we go up another step of another standard deviation, so plus 2 standard deviations, between the 1 and 2 standard deviations, we expect 13.59% of the data to be in that range. If we keep going, a 3rd standard deviation, we expect about 2.15% to be between the 2 and 3 standard deviations. Now I'm going to come back and give you some examples to make this a little clearer in a second. Outside of 3 standard deviations, we expect to find only 0.13%. That's 13 out of 10,000. So very few go outside that range in that direction. And going the other direction, it's symmetrical. So we have the same numbers. About 34.13% here, 13.59% here, 2.15%, and 0.13%. So what on earth does that mean? Well, let's say we have a data set. Let's talk about something that hits home to students. Let's talk about test scores. And let's say that on my Unit 2 test, there is a mean score of 75 with a standard deviation of 8. What that means for this curve. Now the numbers I put in here, these percents, always stay the same. They will never change. From one textbook to another, they might be off by a decimal place or two just because textbooks round them off different. But realistically, those numbers are those percents are the same, no matter what we're looking at, what we're studying. That's what the normal curve is defined to be. But what these numbers here give us, the mean and standard deviation, is they give us the numbers down here. So that mean of 75 means 75 is at the center of this curve. The standard deviation of 8, well, plus 1 standard deviation means we take 75 plus 8 would be 83. A second standard deviation, adding another 8 would be 91. A third standard deviation, adding another 8 would be 99. Going the other way, we're going to subtract the standard deviation. 75 minus 8 would give us 67. Minus another 8 is 59 and 51. Well, what on earth does this mean? Well, let's say we want to know what percent of students score more than 83. Well, we come up here, here's 83. More than that would be going in this direction. So we add up those 3%, and it's going to give us 15.87%. So we'd expect 15.87% of students to score above an 83 on that test. Or let's say we want to know what percentage of students will score below 59 on the test. Well, here's 59 right here. Below that would be this direction. We add up those percents, that is a 2.28%. So only 2.28% would be expected to score below 59. What if you want to know what percent would you expect to score between 67 and 91? Well, here's 67, here's 91. We add up those percents, we get, what, 81.85%, I believe, if we add those all up, those three up. So we expect almost 82% of the students to score between 67 and 91. It's a way of predicting before things happen. If we have 20 students taking the test, well, 82%, that's 16 or 17 students. We expect 16 or 17 out of those 20 students to score between 67 and 91 on that test. Or more importantly, let's say that 75 is the bottom of the C minuses. So more than 75 to get a passing grade. Well, we look up here, here's 75. If we add up those percents on the higher side of 75, they add up to 50%. So that's telling us only 50% of the students are going to pass that test. Don't worry, those aren't the real numbers for my Unit 2 test, by the way. Another example that might be helpful. Let's say that you are looking to move and buy a new house. And you have your heart set on, well, you just decided that what you need for your family, you're going to need a 3-bedroom, 2-bath house. And you've done some research and you found in the area that you're going to move to, the mean price of all of the 3-bedroom, 2-bath houses that have sold in the last 2 years is a mean of $125,000. And a standard deviation of $18,000. So what does that mean? Well, we're going to draw on our bell curve. At the very center of our bell curve is going to be our mean of 125,000. I'm just going to write 125 to fill it in. We can go left to right or left or right first. It doesn't matter. I'm going to go to the right first. I can add 18. So this would be 143,000. Adding another 18 would be 161,000. 179,000. Going the other direction. Subtracting 18, this would be 107. Subtracting another 18, this would be 89. Subtracting another 18 is 71. So again, these numbers down here come from putting the mean in the center, then adding or subtracting the standard deviation as we go each way. What percents go up here? The exact same percents we just had in the last problem. Those percents never change. They're always the same. 34.13, 13.59, 2.15, and 0.13. Same going in this direction. Okay. So now what are we going to use this for? Well, let's say that you find a house that you absolutely love. It has all the features you want. It's just beautiful. And it's priced at $161,000. And your realtor is telling you, you better put in an offer on this house. It's going to be gone soon. What do? Well, if you have this information, you can see that $161,000 is right here. Okay, what good does that do us? Well, if we look at, if we add up the percents on this side, that's 2.28%. What does that percent mean? That percent means only 2.28% of all houses that are 3-bedroom, 2-bath in that area sold for more than $161,000. If we add up the percents on this side, we get 97.72%, which means 97.72% of all 3-bedroom, 2-bathroom houses in that area sell for less than that, which means there's probably a good chance you're going to find a house that you still like for less money in that area. This is, by the way, what we call the empirical rule. Those percents, like I said, never change. As long as it is a closely distributed or normally distributed set of data, those percents will be accurate whenever we know the mean and the standard deviation of that data. Something else that's related to that is something called a Z-score. A Z-score is another way of comparing numbers. What it does, it actually compares between two different data sets. For example, one is to compare height between men and women. Let's say that for females, the mean height worldwide is 63 inches, with a standard deviation of 2.5 inches. For males, let's say the mean height is 69 inches, with a standard deviation of 4 inches. So my question to you is, who is taller and who is more unusual? A female who has a height of 69 inches, or a male who has a height of 79 inches. Now you might be looking at it and say, well, boy, this one here is 10 inches taller. He's obviously taller. But remember, they're from different groups, different populations. We need to compare them to their own groups to compare them to each other. You might also say, well, this person here is 10 inches taller than the mean. This one's only 6 inches taller than the mean. We don't measure it that way. We got to figure out what the distance is. It's kind of like the bell curve. You could have a bell curve that is really wide, or you can have a bell curve that's really narrow. Well, on this bell curve that's really narrow, a point out here is way more unusual than a point out here on this narrow curve, or the wide curve, because the wide curve tends to be more spread out. And the z-score puts a number on this. So the z-score is found by taking the number, subtracting from it the mean of the population that it belongs to, then dividing that difference by the standard deviation of that population. So for this one, she is 69 inches tall. We subtract the mean of 63, and we're going to divide by 2.5. So 69 minus 63 is 6. Divided by 2.5 is 2.4. What that is saying is that this person here is 2.4 standard deviations taller than the mean for that group that she belongs to. So now we're going to do the same over here. Find the z-score. Well, this person is 79 inches tall minus the mean of 69 inches divided by a standard deviation of 4. Well, 79 minus 69 is 10. Divided by 4 is 2.5. This person is 2.5 or 2.5 standard deviations above the mean for their group. So now we can say that this person has a more unusual height. They're taller. But just barely, because it's 2.5 standard deviations compared to 2.4 standard deviations. The fact that this number is positive, that the z-score is positive, indicates that that value is above the mean. Let's look at a case where the value might be below the mean. Let's say that you are a supervisor at a retail establishment, and you have been charged with firing one of your employees. And you have it narrowed down to 2 different people, Bob and Steve. You've decided that they're your 2 worst sales employees. You're going to get rid of one of them. And you've decided that whoever has the worst performance in sales the next week is the one that has to go. Well, let's say Bob's sales for the week are $1,400. Steve's sales for the week are $2,600. So does that mean Bob's gone? Not necessarily. We need a little bit more information. If I give you the information that Bob works in toys and Steve works in electronics, that might change things a little bit. Most electronics are a little more expensive, a little bit larger population looking for them. It might be natural for someone in electronics to have more sales than toys. So what we need to do is we need to look at the other people in each department. And let's say that for that particular week in question, the people in toys, all of the salespeople in toys, had a mean sales of $2,200. And a standard deviation of $300. Let's say for the people in electronics, they had a mean sales of $3,200 and a standard deviation of only $200. Now you might be looking at this and saying, hey, Bob was $800 below the mean, he's got to go. Steve was only $600 below. But that standard deviation comes into play. Let's look at the z-score. You guys tell me how to find the z-score here. 1,400 is the value minus the mean of 2,200 divided by 300. So 1,400 minus 2,200 is a negative 800. We divide that by 300, we get a negative 2.67. So negative 2 2/3 standard deviations. In other words, 2 2/3 standard deviations below the mean. Let's look at Steve. Steve's z-score is, tell me what to do. 2,600 minus 3,200 over 200. So 26 minus 32, Negative 600 divided by 200 is negative 3. So Steve is 3 standard deviations below the mean. So who is worse? Steve. Steve gets to go bye-bye. Any questions? Okay. Z-scores, like I said, are used to compare between two different sets of data. Things from different sets of data that can't naturally be compared can be compared using Z-scores. It's also, if you're just looking at a single population, a single set of data, it is what we call a measure of position. You can tell if you have a z-score of a positive 1, that's telling us, pretend that looks like a bell curve. If you have a z-score of a positive 1, that's telling you you're somewhere up here in the distribution. If it's a negative 2, that's telling you you're somewhere down here. It's giving you an idea of your position within the distribution. Now, there's other measures of position that you might be more familiar with other than z-score. Like I said, the z-score really works better when you're comparing two values from different populations. The one that we're most familiar with is something called a percentile. Percentile, any of you that took standardized tests, you might be told, hey, you placed in the 82nd percentile or the 93rd percentile or something like that. So the question is, what does that mean? The percentile is literally the percent of items less than that value. Now, if we're going to do any calculations with percentiles, just like with the median, we have to have the numbers put in order from smallest to largest. So I'm going to give you a data set right now with the numbers in order from smallest to largest. We'll go one more. So there's a data set. This particular data set has 12 items in it. Now I'm going to go ahead and number them. I don't have to do this, but it's going to make the next few steps a lot easier. So there's my 12. N equals 12. We're going to start out with the simpler side of things. If I ask you what number is in a certain percentile, let's find that number. For example, what number is the 80th percentile? Well, just like with the median, we start out by finding the position. That's going to be n times our percentile. N is 12. What's the percentile here? 80. So we're going to multiply by 0.8. The decimal equivalent of 80%, which gives us 9.6. What did we do when we came up with a decimal there? We would round up. Always up. Even if that was 9.1, we would round up. Just because we're asking what percent are below that value, so we can't round down because then it won't be below, stuff won't be below it anymore. We gotta stay higher so that everything is below it. So it's the value in the 10th position is going to be our 80th percentile. So 33 is our 80th percentile. Little side note here: there is another way of doing percentiles. Taking that 9.6 and then estimating what would be 0.6 of the way or 0.6 of the way between those two values. That's how Excel does it if you use Excel for statistics. So if you're trying to use Excel at all and you're trying to kind of save yourself some work and use Excel on the homework, when it comes to percentiles, it will give you the wrong answer according to the method that we're doing. Let's ask ourselves, what number is in the 35th percentile? Tell me what to do. Okay, and we get 4.2. What's that mean? Yep, even though it's 4.2, we round that up to the 5th position, which is going to be 17. The 35th percentile is the 17. How about the 50th percentile? Well, we're going to take 12 times 0.5. What do we get? 6. Since we got an integer there, or a whole number, that means it is between the 6th and 7th. So 6th is 17, the 7th is 19. How do we find out what's between them? Add them together and divide by 2. 17 plus 19 divided by 2 is 18. Now, of course, you could probably figure out that 18 is between 17 and 19, right? If you're paying close attention, you might have noticed the 50th percentile is the median. It's n times 0.5. That's how we found the median as well. So it's the same thing. Well, the next thing we're going to do, I'm going to save myself a little trouble here, and I'm going to copy this set of numbers and bring them with me. So I don't have to keep scrolling back up. So it's just the same set of numbers. What I'm going to ask now is, in this case, what percentile? Let's say your score on here is the 29. You want to know what percentile that is. What percentile is the 29? Well, to find the percentile itself, rather than finding the number that's in that percentile, but to find the percentile, it is equal to the number that are smaller, number that are less, plus the number that are equal divided by 2 over n. Then we move the decimal point to make it a percent. So for the 29, how many numbers in our list are less than 29? 8 of them. So that's 8 plus. How many numbers in our list are equal to 29? 1, right? There's 1 in there. So that's 1 divided by 2. It's always a divided by 2 there. Over n is 12. So 8 plus a half is 8.5 divided by 12. Which is 0.708. Yeah, you run that to the 71st percentile. So this is 71%, so the 71st percentile. How about if I asked what percentile is the 15? Actually, I want to ask the 17. Sorry. Is the 17. So now, how many are less than 17? 4. So that's 4 plus, how many were equal to 17? 2. So that's going to be 2 over 2 divided by, and there's 12. So that's 5 divided by 12, otherwise known as 0.416 or 0.42. So it's 42%. So it's the 42nd percentile. Any questions? Okay. Some of you guys try one. Some of you guys try a couple. Why don't you start out by finding the 65th percentile? Where do we start? Okay, well, first thing we have to figure out is what is n. So n is 10. Then what? 10 times 0.65 because it is 65th percentile. So it is 6.5. So then, seventh number, which is, so 48 is the 65th percentile. How many of you had that? How many of you know how to get it now? How many have no clue and want to go home crying? Okay, well, that's good. Is there anybody that really needs me to go through that again so they know how to do it? Okay, all right. How about this? What percentile is 45? Where do we start? Number less. There are 3. Good. And then there's 1 that's equal, so 1 divided by 2, and that's all over 10. So 3.5 over 10 is 0.35. Excuse me, 35th percentile. Not for this one, because we're asking what percentile is the 45 in, not what is the 45th percentile. If we're given the percentile, the 65th percentile, then it's the 0.65 times 10. If we're asking what percentile is the 45 in, well, that's the 45 isn't a percent, it's a number in the list. And we're looking for the percent. Oops. For a normally distributed set of data with a mean of 42, a standard deviation of 8, what percent of the data would you expect to be greater than 50? So if we draw a curve, 42 is the mean, that's right in the middle, going up by 8, the next one is 50. So we really can stop there if we want to. We don't have to label the rest of them because 50 is the point of interest. Our percents, you got the 34.13%, 13.59, 2.13, 2.15, and then 0.13. This is all we really need. What percent is going to be larger than the 50? If we were to add these 3% up, it comes up to 15.87%. So only 15.87% of numbers in that data set should be larger than 50. What do you think? Doing well? All right. This is a great place for us to take a break, so let's do that.